Well, hello everybody. It's great to see all of you here this afternoon, and I'm happy to be here to speak with you, and I really appreciate the invitation. I think this is a wonderful conference, and I think you all are so lucky to have something like this to be exposed to and talk to other people in your field. I think that's absolutely wonderful. So I'm going to tell you a little bit about where I came from. I'm from North Carolina, right outside of Charlotte, North Carolina, and I was kind of a tomboy growing up. Liked to race and out skate and out bicycle the boys in the neighborhood. But, and I also liked to help my dad work on the car and things like that. Mother said she gave me a talking doll when I was about 5 years old. And she said I didn't play with that doll very much. She said I cut the doll open to find out why she could talk. So that might have been an indication of where I would end up. I don't know. So anyway, my mother was a teacher. And when I was 3, almost 4 years old, she taught out in the county just outside of Charlotte, near Monroe. And she took me to school with her. She taught 1st through 4th grade in one room, and the other classroom had 5th through 7th grade. And so she carried me in her room, and she says, "You can go out and play." I said, "Well, there's nobody out there to play with." So I sat in her room, and I did the work, and so she promoted me to the 2nd grade. And so the next year, I went in the town of Monroe. I went to school there. So I went all the way through school, about 2 years younger than everybody else in my class. So, and the reason, because mother was started in July that year, the reason they did that was because that was a cotton country, and they would plant the cotton early, and then students would start to school early and get out toward the end of September to pick cotton. And that was so, why that happened like that. So anyway, I liked math. I liked math in school. I did okay. I'm the youngest of 5 children. The next one is 8 years older than I am, and the 4 of them are together. So I took algebra in Monroe. Took algebra and did fine in my classes. And when I was in the 11th grade, my parents sent me to a Methodist boarding school in Asheville, North Carolina, an all-girls school. And at that school, the only math that they had that I could take was plane geometry. And so I took plane geometry and fell in love with it. I absolutely fell in love with it. I liked the teacher. I liked the way she taught. I enjoyed it all. And it was actually then that I decided that that's what I wanted to do. I wanted to be a mathematician. I had thought about biology before and medicine, but when I took physical science and some of the math, I realized that it was the physical science and the math that I appreciated and liked so much more than I did the biological sciences. And so when I graduated from high school, I went off to college saying I was going to major in mathematics. Now, I finished high school in 1958, and on October the 4th, 1957, my job at the school was to go out and pick up the newspaper and put it in the library so everybody could see it. I don't know if I have it in the slides or not. But that was the day Sputnik went up. On the headline on October the 5th, 1957, was "The Russians have launched Sputnik. It has passed over us 4 times in the last 24 hours, traveling at 18,000 miles an hour." And that sent shock waves through this country. I was one of the children who went through all the drills in school, hiding under my desk and everything else, because we were afraid that the Russians were going to drop a bomb on us. And so imagine them flying right over us and could drop whatever they wanted while we were asleep. So it sent shock waves. And so there were pushes in this country then for all of the students to take STEM classes. So I mean, we're having it now, but they were very important then. Money was put into STEM programs, so folks would go into the technical area and the mathematics areas. And So that was sort of a big thing in my life that happened. We certainly all remembered that. My yearbook had a space theme that year. We we would always remember that. But anyway, I went off to Virginia to college, and I went to Virginia because I had followed my sisters and brothers through high school in Monroe, and I didn't want to follow them anymore. So they went to North Carolina and Tennessee, and I said, well, I'm going to Virginia. And when I got there, I met all these other students from New York and Washington and Richmond, Virginia, and larger cities. And those who were going to major in mathematics had analytical geometry and calculus and all of those things. And I had plain geometry. And I said, well, I will just start where I am and learn it. That was my feeling. Then my dad wrote, and he said, Christine, in 1958, I don't think that there are that many jobs for an African-American mathematician. I think to ensure yourself of a job when you finish college, you should get a teacher certificate. And I knew my dad was trying to help me. If you hear today about the number of students to go to college and then they can't get a job when they get out, you kind of understand it. But I had also kind of set my mind on being a mathematician. And I had this formula that had kind of clicked in my mind somehow. And I called it P to the fourth power. And it was not unlike some of the hints that were given to you in the last lecture before lunch by Dr. Fing. And mine was perceive of yourself in that job you think would be your passion. And so I had perceived of myself as a mathematician. I mean, it wasn't necessarily aerospace. I had thought about actuarial school. I had thought about lots of things. Math goes long ways, and it's always going even further. So the second P in that P to the fourth power is plan. What do you have to do to be a mathematician? Well, so I had thought about that. Well, my gosh, if all I had in high school was plain geometry, then I had a whole lot of math I needed to take because I just didn't have the background with the math. And so I had thought about that. And the third P is then start working your plan and prepare. And the fourth P is persist. You're going to run into roadblocks, you're going to run into detours, and you got to find a way around a roadblock, come up with some way to get around the detour and everything. So that was P to the fourth power. So I said, well, I know Dad was trying to help me, so I'm going to do what my dad says. I'm going to get a degree in mathematics education. So I signed up for that with a major in math and a minor in physics. I also liked the physics. But I said, what I'm also going to do is the electives that I earn in those 4 years I'm in college, I'm going to take higher math classes for every one of those electives. And so there were two things I did during those 4 years. My second year, I had modern geometry class that I had to have to get the degree in math education. It was taught opposite a class of analytical geometry that I wanted. Well, I had to have that one too. I had to have that for education also. And but you know how students will talk about teachers sometimes? Well, everybody told me that the teacher of the class that was at the same time as the modern geometry class was the better teacher, and that the other teacher wasn't so good. So I said, well, I don't want a not so good teacher. So I'm going to not take modern geometry. I'm going to take the analytical geometry with the good teacher. And that's what I did. And then when I got to my senior year, I still hadn't taken modern geometry. And I had to have that to get a degree in education. And during my senior year, it was taught at opposite advanced calculus. And I said, oh my gosh, I want advanced calculus. So that time, I went to the registrar of the school and said, can I take them both? And they said, yes, you can do that. So I went to the calculus class, and I just got the book for the modern geometry class and read on my own and went to take the test. So I finished both of those classes fine. So my senior year looked like this. It looked like doing student teaching, first semester, student teaching in solid geometry I taught that semester, and 4 higher level math courses. Second semester, I did my student teaching in physics and 4 higher level math classes. So they all kind of ended up in my senior year. But I graduated with a teacher's education degree and 24 extra hours of higher math courses with all those other kids who had come there with the calculus and everything else that, kind of left me behind. But they were my classmates in those other classes. And so I was happy that I was able to do that. But I would never have signed up for 4 math classes my senior year if I had not thought about the fact that I want to be this mathematician and I need a lot of mathematics. And so I think just having gone through that thought process made me go on and sign up for those classes so that I could begin getting the classes that I would need to be a mathematician. So I go off to teach. And as soon as I get to the new job, it was about 60 miles near Highway 85, if you know anything about that in Virginia, North Carolina. As soon as I get there, some of the teachers come up to me and they say, hey, they teach in-service classes to teachers up at Virginia State College, free, I guess. And we all try to go up there on the weekends. Would you like to go? I said, well, yeah, that would be great. So we all go up there. I sign up for another higher math class. The teacher of that class happened to be the head of the math department there. But anyway, I signed up for it. We went through that year going to the classes, and it was great. Everything worked out. After that year, I got married. I actually had a child, and so 2 or 3 years later, I was teaching in another place that was about 80 miles from Petersburg this time. And I was the one that suggested to the teachers in the school, I said, Virginia State teaches these in-service classes. Wouldn't it be great if we could ride up there and take some classes? So, except this year is on Friday night. It's not on Saturday morning. So I got a carload of teachers to go up on Friday night to go up and sign up for some classes, drive 80 miles after work. So we went up and we signed up for the class, and the first semester went well. Well, come the end of the first semester, do you know what happened? Every one of those teachers quit. They said, we're not going the second semester. I said, oh my gosh, I can't quit. I have got to stay in that class. I have got to finish that class. And, and I'm thinking, I really don't want to be driving that 80 miles home by myself at night at 11:30. But that's what I'm going to do. I'm going to stay in the class. I'm going to take that class. So I continued going to class the second semester. My husband had gone to Virginia State, and during that second semester, he got a fellowship to get in biology, to go and get a master's degree in biology at Virginia State. I says, oh, wow, that's really great. I says, but then it looks like we might be moving up there. So I applied to all the school systems around Virginia State. And one school system wrote back for a letter of recommendation. So I went to my principal and I said, would you give me a letter of recommendation? He said, of course I'll give you a letter of recommendation, but I want your contract back. I says, well, okay, I'm going to get that job. All right, I give him my contract. He writes a letter of recommendation. And I never heard another word from that county that wrote for the letter of recommendation. So the next week or two, when I go up for my class on Friday night, I go up to my professor and say, well, I'd like to ask you a question. I said, looks like we might be moving here, and I'm wondering if you know of any jobs around here I might look into. He said, oh, you're looking for a job? I said, yes. He says, well, let me take you across the hall and introduce you to Dr. Hodkinson. He's the head of the physics department, and he's looking for a research assistant in aerosol physics. So we go across the hall, and we meet Dr. Hodkinson. And my math teacher, of course, is kind of pushing the job for me. And before I walked out of there, I had that research assistantship in aerosol physics. So that was going to pay for me to get my master's degree and pay a little bit of money to help live on. And so it was wonderful. I when I was taking some of these other higher level math classes, I found myself getting a little upset because all of the pure math problems and everything were kind of in the front of the book, and we never got to the applied problems in the back of the book. And I found out that I really loved the applied problems. I really loved knowing what those equations meant and what they could be used for in the real world. And so I got my master's in applied mathematics. And I did my research working with Dr. Hodkinson in light scattering of non-spherical particles. And as I was graduating 2 years later, I applied to a couple of universities back down in Tidewater, where my husband was. And I said, oh gosh, I should go by the placement office. So I went by the placement office and I told the young lady who I was. She said, where in the world have you been? I said, well, I've been here. Well, didn't you know NASA was here yesterday recruiting? I said, no. She said, well, they were. Here, you fill out this application and you get it back to me as soon as you can, and I'm gonna mail it in. She did it, and 3 weeks later, I had an offer from NASA. So I had an offer from NASA and both of the universities that I applied to. It just seems like things fell into place, but none of that would have fallen into place if I hadn't taken all those math courses in undergraduate school, because I wouldn't have been qualified for any of it. But anyway, my husband is the one who suggested. NASA offered me $9,000. Both of the colleges offered me $4,000. So he suggested I should take the $9,000. So I go off to NASA. And I did not realize I had been hired as a computer, but I was assigned to the re-entry physics branch. And that was the branch that calculates the speed and the angle at which a space vehicle must re-enter the atmosphere so that it doesn't get too hot and burn up, or so that it does not bounce on the atmosphere and go back out into space. They had done all of the Apollo calculations before I got there. But it was the hypersonics complex. Supersonic flow is above the speed of sound up to just below Mach 5. And Mach is how they, of course, named the speeds. That was a man's name who discovered how the flow conditions actually depend very often on the speed of sound in multiples and so forth. And so, and then hypersonic is 5 and above. And you start getting chemical changes in the atmosphere when you're at the hypersonic speeds. And so one of the more interesting problems I had while I was working in some of those wind tunnels around there, if you ever saw a picture of Langley, there are some buildings with huge spheres around them. And that was the building I sat in. Well, those huge spheres were used for hypersonic tests. They would pump one sphere down to a vacuum. They would pump a neighboring sphere. They would put other gas in there. Sometimes it was helium or something. And then they would remove the diaphragm, high pressured air in there. And you would get the air from the full tank rushing into the vacuum at Mach 8, 10, 12, huge speeds. And that's how they would do what they called the blowdown test. The test would only last 30 seconds. Or something like that. And so I was given a problem one time to actually calculate the speeds and the flow quality going in from the full tank over to the vacuum. And I happened to get a little upset with the engineer about that, because he got the equations, the governing equations, and he did a few manipulations with them. He gave them to me, and then I had a system of equations that I had to solve, and I did, and I wrote the computer program and debugged the computer program, and he came in and he said, no, that's not right, So I went through and checked everything again, and he ran it again. I don't know if I changed maybe a little something. He came back and he started laughing. No, that's not right. And when he started laughing, I got a little ticked. And I said, well, look, I have been through this. I've checked everything. I can't find a thing wrong in here. I said, let me see those pages where you got the equations and dealt with them in the first place. So he brought his derivations down there, and I went through them, and I found a sign wrong. And when I changed that sign, those numbers were right. So I did not appreciate him laughing at me like that. But anyway, that was one of my more enjoyable jobs when I was in the computer office. But then I said, you know, it looks like the engineers are working with the same kinds of equations I worked on in graduate school. And I says, maybe it's because they're engineers. I didn't really know what an engineer did. The engineers in Monroe, North Carolina that I heard about drove trains. And so I didn't really know that a lot of them sat at desks actually working with equations, almost just like mathematicians. I said, well, it's because they're engineers and we're mathematicians. Somebody that was there said, oh no, a couple of those men have math degrees. I said, they do? Yes. I says, well, that's what I want to do. So I went to my supervisor and I asked about transferring to the engineering section. And he said, no, that's not possible. That won't happen. So after about 2 or 3 more weeks, I said, I'm going to somebody higher. I made up my mind that I did not want to stay in the computer office, and I would rather go back and teach if that was necessary. And so I said, I made an appointment to go talk to the director. And I said, good afternoon. I'd just like to ask you a question. I said, I'd like to know why a female and a male coming here to work with almost the same background are assigned to such different jobs. You put the female in the computer office, she's working on what the engineer brings her, nothing she has chosen to do. She doesn't give talks, she does not write papers, she can't even get her name on a paper half the time, and she doesn't get promoted. The men are put into the engineering group. They might have been assigned an area, but they're doing research in that area. They give talks, they write papers, and they get promoted. And he looked at me and he says, nobody's ever asked that question before. I says, well, I'm asking it now. And I, after a few more words, went back to my office, and I would say 2 to 3 weeks later, I got promoted and I got transferred. And that was 1972. I had gone there in 67. In the late 60s and the early 70s, the United States, the English and the French, and the Russians were all planning to build a supersonic commercial airplane. And the United States, as a part of getting ready to do that, had scheduled a series of flight tests over Chicago and Oklahoma City. So they got military airplanes, supersonic airplanes. They flew them over those cities, and they had probably banks of people bigger than this room answering phones about the cracked sheetrock, the cracked windows, and the noise that was coming from the sonic booms from all of those supersonic airplanes. And so the United States canceled its SST program in 1971. And not only did they cancel their SST program, they passed a law that there should be no commercial supersonic flight over the continental United States. And that law is still on the books today. That's why you don't see any airplanes flying commercially. Now, military planes, sometimes when they have to fly, they do fly supersonically. Sometimes they do all of the flight testing well, you all are in the West, aren't you? But near the West, in Nevada and California, we always did our flight test in California. Of course, Nevada, lots of the flight tests and everything. So that's where we were. And NASA says, well, we like to go fast. People want to go fast. We ought to have somebody looking at the sonic boom. Is there some way we could reduce that sonic boom such that we could make that acceptable? So, as my first job, and that's just what I just talked about. How is the sonic boom generated? How can one predict the sonic boom? How can the sonic boom be reduced? I don't think they knew about the sonic boom until the first supersonic flight occurred in 1947. And they had a sonic boom. And so there were lots of brilliant researchers who started trying to figure out these answers. You know, how is that thing generated? How can we predict it? And so forth and so on. And so when I went into the new branch, my boss came in with a paper written by Dick Seabass and George, who were professors at Cornell University, with some ideas about how to maybe minimize the sonic boom, and said, I want you to program these equations in here, and you know, so that we can start some work. And so I did. I worked on that for a while. And let me talk a little bit about what a sonic boom is. When I'm talking to a lot of students, certainly even younger students, many much younger than you, I will often use the illustration of a balloon. All of you have an atmospheric pressure on your ear right now, and that's the atmospheric pressure in this room. If I were to blow up a balloon, I am putting more molecules into the balloon. The air pressure in the balloon is getting higher than the air pressure in this room. When I pop that balloon, there is a shock wave set up going at the speed of sound in all directions. And that speed of sound at sea level is 760 miles an hour. When that shock wave hits your ear, the pressure on your ear jumps instantly to the pressure that was in the balloon. And that is the pop you hear. This has the same concept. When the airplane is going faster than the speed of sound, all of the disturbances that it's generating in the air are traveling at the speed of sound the same way. But so the airplane is going faster than the disturbances that they're creating. And so they're going out in all directions. They continue to grow. That's why this cone is getting bigger and bigger. But you get, this is, what do you call it in math, where all of this is like the barrier to all of the disturbances. All of the disturbances are inside that cone. And so because of molecules that are getting pushed out of the way, because of shocks off of the wing and the shocks off of the engines and things like that, all of those things are happening inside that cone. The pressure inside that cone is actually higher than the pressure outside the cone. So if this airplane is flying at 45 or 50,000 feet, that cone is going all the way to the ground. If you were standing in front of that intersection of the cone with the ground, you're in the normal pressure because that cone is not in the ground in that white section right there in front of it. But as soon as that airplane moves a little bit, it's drug over you and you hear the sonic boom. And that's what a sonic boom is. Now, a lot of the military airplanes that were flying, their sonic boom was measured by what we call the far-field N wave, that N up there. That front shock is the difference in the pressure on your ear and the pressure before the balloon and the pressure on your ear after the balloon. So it is the difference in the pressure that you hear. See that left part of that N up there? That's what you're hearing. You can hear the same thing on the back of that N wave too. If the airplane and things are long enough, there's enough time between those two shocks that you can distinguish it. They used to say if the shuttle flew over you, you would hear a boom boom. But lots of times when you hear a sonic boom, you just hear a boom because they're so close together, you cannot distinguish two sounds. It's just one sound you hear. But that is generally how they would measure that delta P and what you hear. So a lot of the work that had been done starting back in the early 50s was work done by a man named Whittam, who tried to relate the airplane and the disturbances with a body of revolution, an axisymmetric vehicle. And they were all trying to relate the area distribution, that A sub E up there, that goes with the airplane. They were trying to relate that with something called a Whittam F function, which they say if you were far enough away from that airplane, you could use an axisymmetric vehicle and get all of the area from it, and it would actually be an excellent mimic of that airplane and all the disturbances created by that airplane. Do you see the slanted line going through there? That's like a Mach cone, and that's a Mach angle. That is a definition of, it's this angle whose inverse sine is the speed of that vehicle over the speed of sound. And it has an angle. In fact, that cone on that airplane was at that angle. That's the angle that you get. So they had the theory that if you had this line, this plane going through your airplane all along its axis, wherever it intersects that, if you then project that to the vertical on that plane and bring it down here and say this is volume due to the area of the airplane. And that's what they've done. And so that's part of the equivalent area due to the volume of the airplane. And that's what the dashed line is going to. They do the same thing with the second force on there. The other thing on the airplane is what keeps it up in the air, which is called the lift. The upper surface of an airplane is curved. As the air flows over the upper surface, it goes faster than the air under the airplane. You end up with lower pressure on top of the wing than you do under the wing. And so the resultant force on the wing is which way? Up. And that's called lift. That is what holds the airplane up. And so the second curve there with A to the E is the lift distribution. And you actually integrate the lift up to that point and plot that as the area due to lift on the airplane. Now, there are some equations, integral equations, that relate F as a function, as an integral of the area, equivalent area, and it's an able integral equation, and you can invert it so that you could also describe the area as a function of the F function. And that's what it does. Now, when that F function is flying, so to speak, it advances according to its altitude. So down here on this fourth figure, you see that the top peak of that F function up there has advanced and it's doubled. And so now what they do is they say, well, we can get rid of this multiple values, which is not real, by bisecting that area, and you end up with the N wave again. That's how they were predicting the sonic boom of the signatures in early days. And they were using all linearized equations. I heard a young lady give a talk this morning on the Navier-Stokes equations and the Euler equations. Well, nobody was solving any of those equations. They were using linearized equations, simplifying them as much as they could to try to get to the answers to some of these real problems. And all of these were supposed to be at a distance, you know. You're not supposed to be able to look at that airplane very closely. It's when you get a distance away from it that they're saying the linearized theories would work. But that was these were theories that had been used ever since they realized that the sonic boom occurred to figure out how they could calculate these numbers. So here you have one of the things that a sharp-nosed airplane, it actually shows you how all of this comes down through the atmosphere and to the ground. And we called that the drag paradox because we see what happens is you got shocks coming off the nose of the airplane, you got shocks coming off other parts of the airplane. And of course you get signatures up there that have lots of jags in them, and then you ultimately get to an N wave. You get to an N wave because all of these shocks coalesce. And every time the shocks coalesce, they get stronger. And that's why that N wave can end up being very big. Well, there was another discovery made by, I think, a man named Jones, who said, well, if you don't want that shock to move, if you want that front shock not to intersect with those other shocks like we see over there, you don't want any increasing of the power of those shock waves, you need to make a lot of area in that airplane. And they said, okay, we're going to make that a Dirac delta function. It's an infinite jump. And then your airplane is going to be very, very blunt in the front. Well, it's pretty good. If you look through there, you don't see any of those areas coalescing with each other. They all attenuate all the way to the ground. But that big blunt nose costs a lot of gas. Somebody was talking about the drag on an airplane. You don't want a big blunt-nosed airplane for the drag. And so that was one of the theories that we had to look at and think about. Should we actually do that? And so that was the idea of the F function with the Dirac delta function was in that area. One of the things my boss has suggested is, well, maybe we should actually make that Dirac delta function almost more an inverted triangle and be able to control that, make it as wide as we could or make it as small as we could to see what it does to the drag of that aircraft when we are designing it. And so that is one of the things that I did to that. And then what you want to do is describe what your minimizing F function is going to look like. And that's what that top curve is. It could be the Dirac delta function and then the flat area, and then you get that. And once you get the Dirac, the F function, you can define your area. And once you define your area, that's where we went to work defining airplanes. So these are some equivalent areas that came out of the program that we ultimately wrote. And the top curve is more like the fighter airplanes that we had today that give the big N waves, but the curves that were coming out of these low boom planes were the lower curves. And so once the code was running, we started designing airplanes. We would design the fuselage and the wing, and then we would calculate the area due to volume, the area due to lift, add them up, and we'd sit down and see how close it was to the target that we were getting to. And you can see that actually the dashed line there, we got pretty close on that one. That might have been after 30 attempts to get there, because the first attempt was probably up there near the first one. But we had to decide, where does the design need to be changed to drive us to that? And that was done manually as we were doing it, and it took us quite a while. But once we got that close, we built airplanes. We sent our designs to the shop, and they built these airplanes out of stainless steel. This one is sort of fancy. I think this design Mach number was 2.7. This one was not quite as fancy. That design Mach number was 2. But we built those models. As I said, they cost about $6,000 or $7,000 because every part of those designs had to be accurate. The dimensions had to be exact, the thicknesses had to be exact, and everything had to be exact. We put those models in our supersonic wind tunnel, which was 4 by 4 feet. And we the model is there installed, and the ground is on the side. That's a pressure probe on the wall, and there's another pressure probe up top where you can't see it. That yellow bar across the back there, it can actually move that airplane a short distance forward in the tunnel. So now you know what a wind tunnel is? Yeah, this is like a big section around the room or around the building with a huge compressor on one end that drives the air through there at your design Mach number. So it would drive the air through here at Mach 2 or Mach 2.7. And that Mach cone on the back of that airplane is now going to form on that airplane, and when it is forward, you're going to read the pressure inside that cone on this bottom pressure probe, and you're going to read the pressure outside that cone up there at that top pressure probe. That's the delta P that we would be seeing. And one of the issues we ran into with this was they started out, they were supposed to, all of these linearized theory things say you're supposed to be a big distance away. Well, this is only 4 feet. When they started doing some of these tests, they were making the models this big, and so that they could be 25 body lengths away from the thing. But our models got bigger and bigger, and we were probably introducing some error into the results that we were getting. But we did this, and we actually used some baseline military planes, like a Delta. We would take a Delta wing and build a model of that. We'd get a big N wave. We would do an arrow wing of a military airplane. We'd get an N wave. But when we started doing these tests on these designs, we were not getting N waves when we got closer there. Of course, the N wave was on the ground, but you could actually tell when it would become an N wave. Now, as I'm saying, as time went along, and I worked on this about 20-some years. We worked on this. As time went along, of course, the computers got bigger and better. Well, computational fluid methods came along that were solving all the equations and so forth and so on. And so you see the shocks here by the dark areas, because you're having extreme pressure gradients in those areas. And we started actually using CFD codes to kind of finalize some of the designs sometimes to make sure we were doing right. Now, one of the things we also worried about was, how do we get all the way to the ground with this? Because that signal, if we're flying at 45,000 feet, that signal goes through 45,000 feet of atmosphere to the ground. And so I also developed a code, a modified method of characteristics, working with some of the professors at NYU in New York. And so that we could calculate all the way through the atmosphere with this computational method and not just a linearized theory method. So we did that. This part of the design was what we were calling the, what time did I start? 1 o'clock? 2. It's time for me to quit, isn't it? It's, okay, so we used the CFD where we could in the later stages of our work. And we were about to say, well, you know, we are getting what we expected to get from these designs and everything. So we said, we're about to stop the wind tone test. And we did acoustics tests. We had a sound booth where people reacted to sonic booms. We also went out to White Sands, New Mexico, and did flight tests and measured the signals in a quiet atmosphere and in a turbulent atmosphere. But we said, okay, we've kind of done what we said we were going to do. Then somebody said, well, you know what, we need to do a flight test. We need to actually do this in an atmosphere. So we went out to California and we borrowed two Air Force F-5s. And we put panels on one of the F-5s that made the equivalent area distribution match that equivalent area distribution that we had gotten as our target when we were doing our research and everything. So you see it looks like a porpoise there, and you can see the signatures. The red signature is kind of the N wave you would get. The black signature is more like the shape when you got a smaller shop in the front and you don't have the big expansion at the top there. But the camouflaged F5 here is at the bottom. The modified F5 is in the middle. There's an F15 at the top, and it is reading the pressures coming off of that modified airplane. And so that's the way you read them. We would read them through the atmosphere. When they did that flight out at the NASA Center in California, you could hear the people in the control room shouting, just like they did in Hidden Figures when John Glenn came back from his orbit around the Earth. And it was successful. And so once we declared this a success, and this was in 2002, we said the next thing that has to be done is, that's nobody's supersonic airplane. Nobody would fly around in a plane looking like that. It was just a sonic boom demonstrator. But what we need now is a real airplane designer integrating an efficient supersonic airplane with a good low boom airplane. And so in 2017, the money was put in NASA's budget to build a supersonic low boom X-plane. And Lockheed Martin has been working on that. And this is the Lockheed Martin design. Lockheed Martin got a contract for $247 million in March. And they are working on this airplane as we speak. They are expecting to have it done by 2021. And once they have it done, they will carry it through its supersonic test, flying around to make sure everything works. They did some low-speed tests at Langley this past summer to make sure it's in good handling qualities even when they're landing and taking off. And then they're going to fly over people like you. And they're going to have you answer questions about the noise. And they claim that it will be just a rumble, that you won't even hear the shock. And so they will collect that data that they'll get flying over people from all around the country, and they're going to give that data to the FAA, and they're going to ask the FAA to consider a rule change so that there could be commercial supersonic flight in this country. That way, Gulfstream, Boeing maybe would build supersonic airplanes, American United would buy supersonic airplanes, and you could fly to New York in an hour or so. But that might not be exact, but that's the theory behind that. That's the theory behind getting there. This is one of the tests in the Langley Wind Tunnel going through its low-speed test. And so that's what I worked on for a lot of years. And once we did the flight test and everything, I went into a career development program at Langley, and I spent 6 months at Lockheed Martin in Georgia working. I spent several months in Washington at NASA headquarters and see how they work with Congress and everything. And after that year of many, many classes and very valuable classes, I was put in charge of a office at Langley that managed all the work we were doing for the other NASA centers. They were managing the money differently, but it was air traffic management, it was computational fluid dynamics, it was working with engines in several areas that we managed the work. And I ultimately managed the education office at Langley. So I ended up my last 8 or 9 years in management, but I had a wonderful career. I enjoyed all of this. I gave talks overseas on the sonic boom work in Greece, in Japan, in Germany, in England, and in France. And so it was one of those times where you're just excited to go to work every day. And I think that was just the idea about the contract being awarded. And so that was great. I am just so proud of seeing all these young mathematicians in this office. I mean, in this room, and what great things all of you are going to do.
Well, let's go ahead and ask your questions for the speaker.
So, if you're flying supersonically, does it sound different if you're in the plane yourself flying?
You don't hear it.
You don't hear it?
You don't hear it.
Doesn't sound like nothing?
It's that difference in the pressure that you're hearing. You know, that cone is all around you and everything, but you've got to have the difference in the pressure to hear that jump. Yes?
If you are flying supersonically, I know that when you're in an airplane, if you dip down, you feel yourself pull up, or the opposite, right? So when you're starting supersonic flight, would you feel like a terrible lurch? Like, would it hurt?
Well, and listen, I have never flown supersonically. But I don't know that it would hurt. But as I said before, they actually did have problems when they were first trying to go supersonically on the difference in the airflow as they went through the sound barrier. I mean, they would always talk about this sound barrier, and they would talk as if you went through it one time and you were outside of it and everything. But it actually, it's hanging on to you as you're doing that. But I think it's a smooth flight. The people that flew on the Concorde, I don't think ever had any problems. Concorde was an excellent airplane. And the biggest problem with the Concorde is it didn't have anywhere to fly, because there were rules all over this country and in Europe and everywhere else that they couldn't fly supersonically as a commercial airplane.
So as the plane slows down, would the cone catch up to the plane and then they would hear the boom, or does the cone kind of disperse as the plane slows down?
Well, the cone goes away. The cone is there because the airplane is going faster than the speed of sound, and everything is within that cone. Well, once the airplane is slowing down, they don't stack up. Those sound generations, they don't stack up anymore, and you get this big jump right up near the edges of that cone. And it's gradual. It's like when I said, you hear a balloon, you hear the pop. Well, when you're going up steps, you get the pressure on your ears changes as much as the pressure about that balloon, but you don't hear anything because it's a gradual change. And that it has to be an instantaneous change for you to hear it.
Maybe one more question.
So you said that they were having issues with windows breaking, especially when they were testing this. Do you know about how far away it can still affect such things like that?
You said
With the sonic boom.
the windows and things like that?
Yes, ma'am.
Well, of course, that depends on how big that delta P is when it hits down. So they're saying this is going to be more of a gradual change than the instantaneous change, shock kind of thing. And so it would not break anything. It would be like a rumble of thunder or something like that.
Okay, before we go on, let's first thank our speaker again, and then I have a quick announcement.